Continuing to our lecture, this is work and energy. Also, power is included in this lecture. So, work is said to be done when a force applied on a body displaces the body through a certain distance in the direction of the force. So, if a body, let's say body lies on a horizontal plane and force is applied to this body and it moves at a distance or a displacement of s, and this is force applied. Okay, so when the applied force, okay, to this object changes its position with the displacement of s, so there is work applied. Okay, so the SI units of work is joule, which is a scalar quantity. So the formula for work is given as force multiplied by cosine theta multiplied by displacement, or simply that is Fs cosine theta, or simply force multiplied by displacement. Okay, so where force cosine theta is the component of the force acting along the direction of the displacement produced. Force can be applied at a certain angle, like for example this angle, so force is applied with a given angle, okay, theta. Okay, so the movement of the object is along this direction. Okay, so that is simply F cosine theta, theta. Okay, and it is multiplied by displacement or distance. So work can be positive, okay, can be positive work, negative work, and also zero work done. When we see positive work, the angle between the force and the displacement is either 0 or an acute angle. So from 0 to 89 degrees. Okay, and negative work, if the angle between the force and the displacement is either 180 degrees or an obtuse angle. And when we say 0, there are 3 possible reasons. Work done can be 0 if no force is applied on the body. Okay, and for number 2, force is being applied to the body, but then the body doesn't move. So that is, although the force is being applied on the body, but it is unable to cause any displacement in the body. And the third reason is both the force and the displacement are finite, but then the angle theta between the direction of force displacement is 90 degrees. So cosine 90 degrees gives you a value of 0. Okay, that is the third reason. Okay. So energy is defined as the capacity or ability of the body to do work. So energy is scalar and its units and dimension are the same as that of work. So the SI unit of energy is also joule. So there are so many types of energy such as kinetic energy, potential energy, electrostatic, magnetic, geothermal, and so on. So some other commonly used units for energy are, okay, you should memorize these conversion factors. Okay, so 1 erg is 10 to the negative 7 joule. 1 calorie is 4.186 joule. 1 kilocalorie is 4186 joule. 1 kilowatt hour is 3.6 times 10 to the 6 joule, or 3.6 million joules. And 1 electron volt, or given 1 eV, is 1.6 times 10 to the negative 19 joule. Okay, these are commonly used units when it comes to energy. So let us proceed to this problem. Illustration 6.1. So how much work is done on the lawnmower by the person if he exerts a constant force of 75 newtons at an angle of 35 degrees below the horizontal and pushes the mower 25 meters on level ground. So solution for this, let's draw a diagram. Okay, so let's say this is the lawnmower and the person applies a force to the lawnmower of 75 newtons at an angle of 35 degrees below the horizontal. Now, and pushes the mower, okay, 25 meters, so the displacement or distance moved by the mower is 25 meters. So the question is, how much work is done on the lawnmower? So using the formula, work is equivalent to force multiplied by distance and cosine theta. So F cosine theta is this one. You can say that is the x component of this force. So F cosine theta. Okay. Substituting the value, force is 75 newtons. The displacement is 25 and cosine theta is cosine 35 degrees. Gives you work done using your calculator. Okay. Gives you 1535.91 joules. So kinetic energy. So this is one of the commonly used energy in physics, and the other one's the potential energy. So let's say kinetic energy is the capacity of a body to do work by virtue of its motion. So the body is moving, so motion may either be translation or rotational. A body of mass m moving with a velocity of v has a kinetic energy of 1/2 mv squared. So this is the formula for kinetic energy: 1/2 mass multiplied by velocity, square of the velocity. That gives you kinetic energy. So illustration 6.2. Okay, so what is the kinetic energy of an 80-kilogram athlete running at 10 meters per second? So for A, what are the given? Mass, okay, mass is given 80 kilograms, running at 10 meter per second. This is the velocity. So the unknown is the kinetic energy. Sometimes on some other textbooks, kinetic energy, that can be written as KE. Formula for KE is 1/2 mv squared. Okay, some textbooks uses this notation, kinetic energy. I used K only for kinetic energy. So solving for problem A, so kinetic energy gives you formula of 1/2 mv squared. Mass is given 80 kilograms and the velocity is 10 meters per second. Substituting the values gives you 1/2 multiplied by mass 80 kilograms multiplied by square of the velocity gives you 4,000 joules, or this can also be written as kinetic energy is equivalent to 4 kilojoules. Okay, now for letter B. The Chicxulub crater in Yucatan, one of the largest existing impact craters on Earth, is thought to have been created by an asteroid traveling at 22 kilometers per second and releasing 4.2 times 10 to the 23rd joules of kinetic energy upon impact. So what was its mass? So the mass of the asteroid. Okay, from your formula, 1/2 mass velocity squared kinetic energy. So based on the given from letter B, velocity is given as 22 kilometers per second. So you have your velocity. and you have 4.2 times 10 to the 23rd joule. That is the kinetic energy. You can construct the formula using this equation by mass is equivalent to twice the kinetic energy all over velocity, square of the velocity. So simplifying, you multiply both sides by 2, okay, then eliminated, and then dividing both sides by velocity squared, so that leaves you mass. So this is the formula for mass. Okay, now substituting the values, that gives you twice the kinetic energy. Kinetic energy is 4.2 times 10 to the 23rd joules divided by 22 kilometers per second. So why did I use 22,000 instead of 22 kilometers per second? So the unit of velocity for kinetic energy is simply in meters per second. So you need to convert kilometer, okay, to meters. So that is simply 22 kilometers per second. So multiply by, in 1 kilometer there is 1,000 meter. Okay, so kilometer will be eliminated, so the unit is meter per second, and that gives you multiplication. So 22 multiplied by 1,000 gives you 22,000. So reminder, velocity is always in terms of meter per second. So the mass of the asteroid gives you 1.74 times 10 to the 15 kilograms. Okay, so for letter C, problem C, in nuclear reactors, thermal neutrons traveling at about 2.2 kilometers per second play an important role. What is the kinetic energy of such a particle? So kinetic energy, so you know the formula is 1/2 mv squared. Now what is the particle? Okay, the particle is neutrons. Okay, so the velocity of the neutron is given as 2.2 kilometer per second, or that is 2,200 meter per second. So the formula, okay, kinetic energy is unknown, 1/2 mass velocity squared. So the velocity is given. How about the mass of the particle? Mass of the particle or mass of neutron? So take note that mass of neutron is 9.11 times 10 to the negative 28 kilograms. This is a constant value, so you need to also recall mass of protons, mass of electrons. Okay, so mass of neutron is given. Okay, substituting the values to the given formula gives you 1/2 mass is 9.11 times 10 to the 28, and the velocity is 2,200 meter per second squared. Okay, that gives you 2,204.62 times 10 to the negative 24 joules. Okay, so based on these problems, they are only direct substitution from the given formula 1/2 mv squared, but then you can also solve for mass, like for problem letter B, or also you can solve for the velocity. Okay, so formula for velocity based on the formula will give you what? Okay, so this will be the formula for the velocity. So the square root of twice the kinetic energy divided by mass. Illustration 6.3. Okay, I'll just leave this problem as your activity, one of your problem on your activity for the day. Okay, So work energy theorem. So to simplify this formula, change in kinetic energy will be equal to K2 is final, okay, final kinetic energy minus initial kinetic energy. Okay, so work done by all the forces, conservatory and non-conservative, external or internal, acting on a particle or object is equal to the change in kinetic energy of it. So change in kinetic energy is equivalent to final kinetic energy minus initial kinetic energy. So kinetic energy of body is always positive irrespective to sign of velocity. So negative kinetic energy is impossible. So the answer for the change of kinetic energy is always positive. Power. So power is defined as the rate of doing work. So rate of doing work. So if an agent does work of W in time t, when its average power is given as work all over time. So this is the formula for power. Okay, the shorter is time taken by a person or machine in performing a particular task, the larger is the power of that person or machine. So power is scalar in quantity. SI units is uh, work. One work is equivalent to 1 joule per second. Okay, so 1 watt, 1 watt is equivalent to 1 joule per second. So watt is equivalent to joule per second, where work is in joules and time is always given as seconds. So if time is given to minute, you need to convert that to seconds. Similarly, if time is given to hour, you need to convert that to second. Okay, so take note that power is joule per second. So work per unit time. So instantaneous power. Okay, so F derivative of displacement all over derivative of time. Okay, so that is can be written as force multiplied by velocity. Unit of force is Newton. Unit of velocity is meter per seconds. Okay, but then Newton, okay, meter is also joule, or that gives you force or work, okay. Some other commonly used units, so you need similarly. So 1 kilowatt hour is 1,000 watts, 1 megawatt is 1,000,000 watts, and 1 horsepower is given as 746 watts. So you need to remember this conversion. 1 horsepower is equivalent to 746 watts. Okay. Illustration 6.4. So how much power must an automobile engine expend to move a 1,200 kilogram car up a 15% grade at 90 kilometers per hour, as shown in figure 4.1. So assume that 25% of this power is dissipated, overcoming air resistance and friction. So if power is 100%, 25% of that is used to dissipate or overcome air resistance and friction along the car's wheel. Okay, so in all, only 75% of the power expends to move the 1,200 kilogram car. So the mass of the car is 1,200 kilograms. Okay, its velocity is 90 kilometers per hour, and a 15% grade. So when we say 15% grade, you can calculate its angle using that given. Okay, using the formula tangent theta is equivalent to 0.15. Later on I will explain. So the solution. Okay, so at the constant velocity, there's no change in kinetic energy. So the net work done to move the car is 0. Therefore, the power supplied, okay, that is the net work done. But the power supplied by the engine to move the car equals the power expended against gravity and air resistance. By assumption, 75% of the power is supplied against gravity, which is equals to power is force multiplied by velocity, and that velocity is against gravity. Okay, so the acceleration due to gravity is needed, so force is equivalent to mass multiplied by acceleration. Recall force, mass multiplied by acceleration, but then it opposes the gravitational force, so acceleration is due to gravity, vector g, or multiplied by vector velocity. So simplifying that equation, so gravitational pull, okay, so velocity, okay, velocity, so sine theta, this one. Okay, so the theta or the angle of inclination is given as tangent theta equals 0.15. So simplifying using the formula, power is equivalent to a mass, gravitational acceleration, velocity, sine theta. Substituting the given values, power used is by the engine is 75%. Okay, 25% is used to dissipate or overcome air resistance and friction. Okay, so 75% is the power supplied against gravity. So it will be equal to mass, acceleration due to gravity, velocity, sine theta. Theta is arctan of 0.15 from this equation. Solving for theta. Okay, this will be the value of theta. Now substituting all the values, so that will give you solving for power. So mass is 1200 kilograms, acceleration due to gravity 9.81, velocity 90 kilometers per hour, right? So velocity is always in meter per second, so you need to convert this to meter and hour to seconds, so that gives you 90,000 per 3,600 seconds. Sine, okay, theta, then dividing both sides by 0.75. okay, then using your calculator, power is given as 58,208.79 watts, or can be written as 58.209 kilowatts. So this will be your final answer.